design doesn't belong to one discipline. Design is an interdisciplinary science where you combine mechanical engineering, electronics, computer science, physics, chemistry, and so on.
We do have a wide variety of labs in the department which give the students training on what are the essential elements that are required for design.
In other words, we wanted to bring the joy of engineering. There are two things in this. One is we wanted to give the fundamentals of design as an undergraduate program and then bring domain knowledge to the postgraduate program. Straight away go to the applications and teach the practice of design through an applied design process or product.
The students have to spend an entire semester in the industry, and with this they are able to integrate their learnings with industrially relevant problems. The actual process of creating new designs requires a special set of skills which we promote in our department.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Has been privileged to host many international students from all over the world. Most of these students come for their exchange programs to either do their coursework, research work, or their thesis for a period of 6 months to 1 year.
I came here with a lot of doubt about being in a different environment, but a pleasure of being in this place. In all my courses, I found wonderful friends who helped me, and I never feel alone or being outsider.
I came here to IIT Madras in searching opportunities, and I've been given the opportunity to work in testing the main sensor of the satellite. This is just one of the biggest projects that IIT Madras is holding nowadays, and I'm really happy to have chosen this opportunity to come here.
The campus is an amazing place. There's so much to do. If you want to do some sports, there are many options. If you're hungry, you can find several food stalls, juice bars and cafes at each corner. The library is a good choice if you want to do some work done, especially when the weather is getting too hot.
Let's do great things together.
Now, the mouse brain, in terms of evolution principles, is relatively simple. Now, the human brain will be a lot more complex than this. It's a lot more area and a lot more denser area, lighter areas, and so on and so forth. So the Center of Computational Brain Research at IIT Madras is designed in a way where we form the interface between biology and engineering.
Talking about engineering in spirit, most computers even today rely on the architecture laid out by von Neumann in 1945. And the problem with that is it's almost impossible to make computers any more faster than what we have already achieved today by making smaller and smaller transistors. But the study of the human brain enables the possibility of an altogether new kind of computer modeled on the brain itself. That's the future.
Hello and good evening to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 26th webinar from the IRIS webinar series. My name is Richu George Philip and I'm a part of the Office of Global Engagement. From the Energy, Propulsion and Renewables Technology Cluster, the research initiative presenting today is Advanced Gas Turbine Engines led by Professor T.M. Muruganandam. Professor Muruganandam did his BTech and MS in Aerospace Engineering at IIT Madras. He then went to Stanford University, Mechanical Engineering for an MS, where he learned spectroscopic diagnostics. He did his PhD in Aerospace Engineering from Georgia Tech, USA, where he worked on combustor flame stability and combustion diagnostics. After that, he joined Aerospace Department IIT Madras as a faculty member and has been here ever since. He has been working on diagnostics in combustion and high-speed flows. He is a part of NCCRD and MHRD Center for Non-Intrusive Diagnostics. He is now the principal coordinator of this IOE research initiative. He has guided 20 research scholars, authored over 35 international journal papers, over 85 international conference papers. He has 5 patents, 2 of which have been commercialized. Joining us as the moderator today is Professor Tim Lewin. Dr. Tim Lewin is a Regents Professor, the David S. Lewis Jr. Professor, and the Executive Director of the Strategic Energy Institute at Georgia Tech. In this capacity, he manages Georgia Tech's overall strategy and external relations for its 120 million per year energy portfolio. He's also founder and CTO of Turbine Logic, an analytics firm working in the energy industry. Professor Tim is an international authority on clean energy and propulsion, and his work has contributed to numerous commercialized innovations in the energy and aerospace sector. He has authored 4 books and over 400 other publications. Current and past board positions include governing advisory boards for Oak Ridge National Lab, Pacific Northwest National Lab, and the National Renewable Energy Lab, appointed by the DOE Secretary to the National Petroleum Council, and board member of the ASME International Gas Turbine Institute. He is an elected member of the National Academy of Engineering, a fellow of ASME, APS, and AIAA, and foreign fellow of the Indian National Academy of Engineering. Major awards include the AIAA Lawrence Perry Award, AIAA Pendray Award, and ASME's George Westinghouse Gold Medal. We also have many of our IITM faculty on the panel today. Thank you to each and every one of you for being with us today. Also extending a warm welcome to the GE team that's here with us. We're very glad that you could be a part of the webinar and be a part of the research initiative. So before we start, a note to the participants, please use the Q&A to enter your questions and upvote questions that interest you so that the moderator can prioritize them later. Over to you, Professor Muruganandam.
Thank you, Richu. I'll share the screen. Hello, everyone. Welcome to this webinar on Center of Excellence on Advanced Gas Turbine Engine Technologies. Apparently, Kamlesh Hatwa is not currently able to join us, it looks like. So I can cover for him, not a problem. I would like to start with thanking our chairman moderator, Professor Tim Lewin, again for agreeing to join us here. Thank you, Tim. So we'll start with, where is the link? Okay, this is our team. I am having this screen, I have to collapse it. Okay. Okay, so this is our team. There are like around 10 people in here. 3 of us are aerospace department. That's me, and this Satya Chakravarti. Tim Lewin also knows him. Nagbhushan Rao. We 3 are aerospace department. There is Kritika, Sesadri Shekhar, and Piyush Shakya. They are from mechanical engineering department. Satya Seshadri and Arul Prakash are from applied mechanics, and Kamlesh Hatwa and Krishna Vasudevan are from electrical engineering department. So it's a multidisciplinary program as it is supposed to be for a gas turbine engine. So I am not going to go into details of this slide. I just want to show here that there was a survey conducted around 2015 which showed that unless we do something about carbon emission, CO2 emission, it's going to be pretty bad. That's the main idea of this. But I'd like to show that aviation has been handling 2% of this global carbon emissions contributions. And from here, if we don't do anything, it's supposed to follow this particular curve up to 2050. If we modify the fuel that is being used in the engine, then it may be flattened out. If we use something like CNG, then it may get flattened out like this. And then if we go for some other fuels, alternate fuels, probably try and use hydrogen-based fuels, these things will bring it down even lower, and we will hope that we can get to 50% of our current state. That's the idea that's given by this particular plot. So there is a continuous race for achieving carbon footprint among the gas turbine industries. If you look at it, they're all telling that they'll use some kind of alternate fuels or use hydrogen blends. And then they say like by 2035, they'll have engines operating with hydrogen blends and maybe fully hydrogenized by 2050. So that's one direction that we need to push the gas turbine technologies. Next thing is everything is getting electrified nowadays, right? Including all kinds of engines. So why not gas turbine engines too? So we are looking at starters for gas turbine engine instead of using compressed air for starting the shaft. Next is seal performance is typically done only by computational methods. Now we are going to go do some experimental work on that, and that is the other part. So what are the main changes that the industry will face if we are going to implement these? What we'll see is we'll have to inject gas instead of liquid. Not a great deal, but we need to think about how it works. It's not the same spray nozzle. If we have hydrogen, it's going to have higher temperature, higher flame speed, burn rate will be higher, heating rate will be higher. All these will cause temperatures being much higher. And that actually means that you need to have better thermal management. And one more thing that will happen with the higher heat release rate would be like your work output per kilogram of fuel will be higher, which means the cycle will be different. It may end up with a higher pressure and higher RPM for the whole gas turbine engine operation. And then we need to worry about the seals should be able to operate at higher heating rate and at higher RPM. So these are all things that we need to worry about. Next thing is if we have to have a starter that's at a gas turbine engine starter, then we need to worry about one good thing is we will have less core air being used, but we need to think about how are we going to manage this? What am I going to do with it while it is not being operated? All that will be taken care of in this. We are thinking that it will decrease the number of components in the gas turbine engine. The 4 verticals in this particular gas turbine initiative that we are having are first thing would be the gas turbine combustor, the predominant effect of making it hydrogen blend or pure hydrogen that will be studied here. Next would be to handle the heat that's generated. It will be like heat transfer as well as waste heat recovery that will be done in this vertical B. Then there is vertical C that is on high temperature, high speed seals. That will be handling what's happening inside the engine inside here. And then there is starters, which are going to be either working as a starter or as a generator. That's the idea of that particular vertical. And then overall goal through all of this is to work as close to realistic conditions as possible while maintaining academic rigor. So we'll go into details of each of these. First vertical is Combusor Technology. And here we're going to say that we'll generate some combustor configurations which will work with hydrogen or hydrocarbon blends or probably alternate fuels like SAF, etc. with making sure that we have low emissions, very good operability and durability of operation. All that along with we have to now be able to test this combustor. So we create a rig like this, which has like high temperature air incoming at reasonable pressures. So we are creating a test condition chamber where we will just have this test combustor, which can be just plugged in and tested. That kind of configuration is what we are envisioning right now. And we will have to have a blending station outside, which will blend the fuel if it is going to be hydrogen hydrocarbon blending system. And then we have to also make sure that we have continuous flow of at least 1 kilogram per second, 10 bar, 600 Kelvin air that's supplied, along with whatever equivalence ratio, air fuel ratios that are supposed to be done for each of the tests for the particular combustor. While we are putting that in there, we have to use advanced laser diagnostics like PIV, chemiluminescence, etc. in there. And We are also going to have more models being updated for hydrogen blends, etc., up to higher pressures than what even can achieve with this test. Okay. The deliverables for this vertical would be that particular rig, which is a plug and test kind of rig with as close to industry conditions as possible. And then we will also arrive at some few configurations for combustor up to tier level 2 to 3 kind of situation. And we will get a lot of benchmark data which can be used to modify combustion models if necessary. And after the first phase, that is 2 years, after that, when we go to future, we are planning to establish the full center in the research campus, which is outside IIT Madras current campus. And then we will establish a full facility with higher than 10 bar pressure, higher than 1 kilogram per second, and try and achieve up to 800 Kelvin temperature of air supply. And in the future, we expect that we will have collaborations from other power generation gas turbine industries, or maybe this combustion model will be, of course, it should be useful for all the other power and automotive industry as well. When you go to next generation heat exchangers, here we will find that this is required primarily because of the high temperature that is produced by the hydrogen combustion. And so we need to have an advanced cooling system because the heat release rate is going to be higher. And so we are planning to use the supercritical CO2 based cooling devices, and we will generate new next generation heat exchangers, which are all going to use supercritical CO2 as the coolant. You can see some of the coupons that are on the left here, which are basically showing this is the kind of thing that we are planning on doing. And phase 1 deliverables will be first create a test rig where we can test this. Then while that is going on, we'll be developing some coupons for heat exchangers, test that hydraulically as well as heat transfer wise. And then all this is done by additive manufacturing. And then we'll go take this knowledge, go into prototype development, and then we'll go and check whether our prototype is working well. We'll go and test it at full scale testing. This is the goal. And after the first phase, we are planning on extending it to waste heat recovery using this SCO2 cycle. You can see on the left, and then we can also add organic Rankine cycle to the bottom of it to make it even more efficient. And then we are hoping that we will also make some contributions in the supercritical CO2 turbines and compressor design. As you can see in the bottom, there's some work going on. After all this, we are thinking that there will be future collaborations which will come up in terms of heat exchangers and heat pump design and all that. And this will be useful for oil, gas, power industries, and also be useful for turbine and compressor manufacturers. Next is on seals performance. This is third vertical. Here, the technology that we are going to look at is actually, can we evaluate the seals very well? And for this, we need to have a test rig. This is the rare thing that's happening around the world. There's not many rigs that are available. And so we need to have a rig where we can test this at close to reality conditions. So we are going to have high pressure, high temperature air that's coming in inside, and then we are going to test this particular air going through the seals at the close to actual RPMs conditions. So the typical rig would look something like this. You can see the seals are around here. My mouse doesn't seem to work suddenly. Okay. So the seals are around here. This is what is depicted is actually a simple labyrinth seal kind of depiction. So some seal like this, the air that's coming in is going to go through this through very small gaps, and that's what it is supposed to seal. That's the idea. So we are trying to have CFD models. Of course, people have already done work on that. There's a lot of literature on CFD work. The main thing is we'll generate some seals and then we'll go put it in there, test it, and see if it performs well at these conditions. And then that will also go into model development. What are the challenges? It's actually high-speed rotor, high temperature, high pressure, and clearances are very, very small. Okay, these are the typical challenges. So we have to be able to assemble this very well without damaging the seals and then test them. While testing, we are going to actually actuate this stator units, which are going to change the clearance between the stator and the rotating seal. And that is actually the crucial thing we need to check. And then it's supposed to be creating instabilities, etc. And then we have to measure what is the actual force that is generated in the rotor based on some particular set of instrumentation which we need to carefully align in there. That's the challenge in this particular rig. So we'll try and make this rig in the first phase, in the first 2 years itself, at close to high pressure and temperature conditions. And we also, there is some parallel work going on in CFD, as you can see on the left. I don't want to get into that right now, want of time. We'll say that we will try and reduce the rotordynamic forces in seals and try to give some particular configurations which are useful for these conditions of operation for the future next generation engines. Okay. This particular capability will actually be promoted into the CFD version as well after the data is given, and then we'll get engine manufacturers to see that it will give you fuel economy and weight reduction. Okay, I'm assuming that Kamlesh Athwa is not there, so I'm continuing into this particular part. This particular aspect is like electrifying the starter generator for the gas turbine engine. So typically we'll use compressed air for starting the engine. Instead, now we are going to have batteries, which will be converting that battery energy will be converted by a converter into a AC, which is going to drive a AC motor, which is going to run the shaft initially. But once the engine starts operating and starts giving shaft power, that's going to be converted into a generator instead of a starter motor. And then that will produce electricity, which is now going to be converted back to DC and stored in batteries or supplied to the aircraft in terms of, say, a primary power distribution system that's present there. The voltages are given out here. So, and then this primary power, this thing is supposed to have some variable frequency. We'll just ignore that for now. They are using silicon carbide based inverters inside there, which is supposed to give higher energy efficiency and give very good compactness inside the circuit. And then if you look at the maximum generator speed that they are targeting, it's around 20,000 RPM. Targeted system efficiency is supposed to be more than 90%. In the first phase, they are going to work with just make the technology architecture, design the whole thing, and go only on paper design, but test it simulation wise, and then go all the way up to TRL3. And then after that, after the first 2 years, first phase, they'll go into prototype development and then test it, extend it all the way up to TRL5. That is, they do repeated tests in there. And then we'll hope that this particular technology will be taken up into the engine. And in that case, it may also be useful for the other sectors based on this particular architecture. Other transport sectors may also be using it. We have a major collaboration partner, that's GE. They are GE Aviation from Global Research Campus, Bangalore, India. They are interested in all the 4 verticals as of now, and they have given support in several sense, like they are giving direct cash contribution for supporting student hiring and also operational budget. And they are also giving in-kind contribution in terms of design support and also fabrication support for some of the special fabrications. Opportunities for others, there will be webinar series for dissemination of information. There will be internships that are possible in this center. There will be collaborative efforts that are possible with other universities if others are interested. There is international collaborations wise, I'm going to say that there will be webinars which we will be organizing after this further. And then there will be other collaborative efforts which will be encouraged. There is a new thing that our director has introduced, is this young international faculty. This is like somebody who is currently at a postdoc level and they are interested in joining a faculty job in the center, that they can do, and they are paid reasonably well in this center. And then there is also student exchange programs with different universities. That is also welcome for these centers. This is the last slide I have. I just want to say that this is a unique center which has all these key technologies which are needed to push the gas turbines into a new regime. And I'll just say that there are 4 verticals. Each of them individually can be industry oriented, and several industries may be having spin-offs from these technologies and they can use it. Other than that, there is also models developed which can also be useful for future predictive capabilities. And we will have some test beds where we can test most of the things at close to full scale conditions. And we may have it in the new campus at even higher conditions for phase 2. Okay, that's all I have. Now we can go into questions mode.
So Murgy, are others going to give talks, or is now where I start moderating?
Oh yeah, it's your turn, Tim. Dr. Kamlesh Hatwa couldn't join. It looks like I talked for him as well. So.
Oh, okay, great. So what I should do now is just for the remaining, I guess, 35 minutes, have a moderated Q&A with the attendees.
Yep, I guess so.
Okay, great. All right, well, thank you for the invite. This is a really exciting program. I enjoyed the video. I have been on the IITM campus, I guess, 2 times. And I had, well, I had hoped to be there last year, but with COVID, it didn't work out. But, I have deep respect for the Institute and all the partners on this call, and this is a really exciting initiative and consortium. So I'm delighted to just be learning a little bit about it as well, and to hear this nice presentation from Professor Muruganandam about it. So I guess what we'll do is you will see in the chat there's opportunities to ask questions. I have some of my own questions, and I'm going to be answering some of these, asking some of these questions, and then maybe merging some of these and asking some of my own. So maybe I'll start with this question around sort of hybridization. So you talked a little bit about hybridization around electrification, but there's also a question around hybridization with fuel cells. Can you just talk a little bit about where and how, or whether that's in scope, or whether you guys have thought about fuel cell integration and so forth?
Okay, currently we are not working on the batteries part of the problem. We are working on the portion after the batteries. So fuel cells will be sitting out there, right, in the fuels batteries side. We are looking at the architecture after the battery till the shaft rotating. That portion is what we are focusing on in this particular center. I believe there are other centers in this Center of Excellence Institute of Eminence scheme itself. There are centers that are working on batteries development. So we will leave it to them, I think. But I guess if it is energy efficient and compact enough, we will plan on using that as well.
Yeah, and I think the spirit of the question was there's been some work on integration of fuel cells and gas turbines to get higher efficiencies than either can do on their own. I think that was the question.
Okay.
So, yeah, maybe I'll move to this question. Just on talk a little bit more about how you're recovering the heat energy, with these concepts.
This is related to the thermal management, is it? Is that the question? Or
yeah.
Is it batteries?
Let me take that question. In terms of heat recovery, as I saw in the Q&A, there were a couple of points on thermoelectric systems and other kinds of opportunities. So the state of the art of thermoelectric does not really allow us to recover much of the energy. So the more commonly employed techniques are the organic Rankine cycle based systems. And one of the key challenges for that in terms of markets such as India, where the ambient temperatures are fairly high, is the low efficiency. So that's where supercritical CO2 is being looked upon as one of the working fluids, both for heat recovery from the exhaust and also on thermal management of the high temperature secondary cooling because of the combustion of hydrogen. So I think though we are agnostic to looking at other options, but it appears like SCO2 is one of those areas that's getting fairly good amount of traction in terms of both turbine cooling and also on heat recovery systems.
Here's another thermal management question just around transpiration cooling and using some of the fuel. Is that a viable method for getting to higher temperatures? And maybe if you can just chat a little bit about that. I guess a little bit like what it's done in rocket systems.
Yeah,
okay.
Muruganandam, you want to take it?
Yeah, I'll take it. As in, like, if we have fuel, especially hydrogen, burning very close to the wall, I think it will increase the temperature near the wall. That may not be a good thing. Yes, of course, it will.
Let me stop you. The question is more around thermal management. That right now hydrogen is used in power stations for cooling. It's most gas turbine power plants or coal power plants use hydrogen already today. They don't burn it, they just use it for cooling because of its specific heat. So I think the question was more focused around the use of hydrogen, use of the fuel itself as part of the cooling scheme and thermal management scheme.
Okay, it's not used as transpiration then, right? You're telling it's like used as in rocket engines, just along the wall, not transpiration.
No, Murgi, this is more towards the secondary cooling, the turbine, the blade cooling holes, and the secondary cooling where you have the compound injection of cooling flow. At this point in time, we are not really sure if hydrogen is something that can be used inside of gas turbine blades for secondary cooling. If that was the question, if I may, I think if I got it right.
Is that supposed to be in the turbine? Then it could be dangerous also, right?
So there are secondary cooling holes in the turbines where you do inject, as I said, compressed air or any other cold air to get the temperatures of the turbine blades lower than the melting point, close. I mean, these are secondary holes that are inside all over the turbine blades. So in that particular holes, sometimes you can use the fuel itself to cool, because if you utilize any other fluid, you are introducing non-condensable, non-combustible gases. So there's some amount of work that's done on introducing fuel itself for cooling. But at this point in time, the way we are looking at it is using supercritical CO2 as a moderator, because supercritical CO2 also has similar high heat capacity and it can do fairly effective cooling, and that has been shown in many recent amount of studies. So that's one of the areas that we are exploring, because it's also safer to handle.
Great. Let me shift gears away from a technical question, which is a number of questions around internships and how people can get involved. Can you guys talk about how people can get internships?
Internships will be, you have to contact us directly, as in the professors. You just drop an email, and when the position opens up, we'll just tell you. We are currently in the initial phase, right? Just maybe in 2-3 months, we'll have enough stuff to do, and then we can distribute it to some interns, and there can be internships possible.
So there are two. In addition to that, there is one more standardized process where every year IIT Madras offers these summer research fellowships for undergraduate students from other institutes other than IIT. So it is a nationwide process. So you can also look out for those processes where we will also be having a couple of projects in that pool as well. So there are two opportunities. One is you directly write to us, and as and when the projects get on board, we will be picking up a few. And there is a standard summer research internship, which is for a period of about 3 months, which you can participate in during the vacation period next year.
Okay, great. Thank you. Can you talk a little bit about, obviously this is a gas turbine focus, but are there going to be, I guess, are you guys going to be thinking about some other propulsion applications like SCRAMjets or supersonic devices?
I do SCRAMjet studies. That may not be coming under this center, I think. We do supersonic combustion studies in our lab, but that is not related to this. We are having a transparent supersonic combustion rig in our facility in the NCCRD. That's not related to the gas turbines focus, I think. Yeah.
Okay. Maybe just talk a little bit about kind of the tech. You used the word TRL5 and kind of tech transfer and things like that. Can you talk a little bit more now about the kind of your strategy, where and how GE will be engaged and some other partners? Because there's some questions here around just clearly India has a long, very distinguished history in gas turbine development, but just the idea of actually seeing these innovations making it into the marketplace.
Okay, I think Mayur will be a better person to take that question. Is Mayur around? I just saw him.
Yeah, hi, Professor Murgi, can you hear me?
Yeah.
All right. So first of all, congratulations to the IIT team, for taking this step, and thank you for inviting us and having us as the collaborators in this. So we've been working with IIT on multiple projects through this, over the last few years, and our engagement has been to basically advance the understanding of technology and then work so collaboratively so that we are able to get some of this technology into our products. And that's what our focus will be as we look on developing these technologies in future. GE recently announced a huge goal on sustainability and through its RISE programs. And we would be looking to support IIT in the best way we can to make sure that some of these technologies are ready for industrialization standpoint. So really looking for IITs to take this forward, and we are there to support and help as best as we can through our engineering center in Bangalore.
Are there I guess, have you maybe talk a little bit about some of the internships and will students be working in Bangalore, as part of the center, or will there be summer internships or things like that?
Yeah, so the idea is that, from our standpoint, I think it's primarily the students working in Chennai in the IIT campus. And we would be happy to have them work with our team and visit our Bangalore site as needed. But primarily, I think the action happens in IIT.
Okay, great. Let me so let me move back to some more technical questions. Maybe let's just talk about the hydrogen itself, where it's coming from. Are you looking at? Maybe just talk about, are you looking at onboard hydrogen production, or would you just be taking, I don't know, cryogenic hydrogen that's stored on the plane, or maybe just talk a little about the production side of things.
Okay, currently we are trying to enable the combustor technology right now. Yes, currently I believe there are these two technologies that are being talked about. One is like onboard hydrogen production using electrical energy coming either from solar or coming from the engine itself, which I think is detrimental. But the other aspect, storing it, I think will cause more trouble. I think it should be onboard production, but I'm not the expert on that right now. I'm going to create this technology so that people will think, yes, there is combustor technology. Now we just have to work on the tanks that are coming up. Yeah.
But onboard production from what? What would it be coming from? Like ammonia or natural gas or some liquid fuel?
Ammonia is a nice option, except for the NOx if we can control it. So there is also electrolysis, yes. Ammonia is easy to store, is what I hear. Sorry?
Okay. You mean actually carrying water aboard the plane? Is that what you're saying?
Yeah. The ammonia is also easier to carry. It also gives you some energy in the process of producing water. So.
Yeah. Okay. Well, while we're talking about that, there's a couple of questions just on the carbon. You know, one of the large goals of this program is around CO2 footprint reduction. Can you comment a little bit on the carbon footprint of hydrogen production?
I did not do the calculations on this particular thing, but I feared that there will be such a question coming up, and it came up. I'll just say.
So let me add that in terms of the economics as of now in India, the green hydrogen production is at anywhere between 800 to 900 rupees per kg, which would be about what $15 per kg, $15 to $20 per kg. Not on green hydrogen, that's on black hydrogen. Black hydrogen is from coal. So as of now, since it's mostly an industrial fuel, it's mostly reformed at the site, specifically somewhere near the steel mills and the places where it's being used. We have not had such a big hydrogen infrastructure, but the government's hydrogen energy targets are to get green hydrogen to anywhere between $4 to $5 per kg within the next 2 to 3 years. That's the target with these mega electrolyzer kind of projects. So with that, in terms of propulsion, given the lack of availability of natural gas in India, hydrogen as a fuel for gas turbine would already be attractive for at least peaker plants and stationary gas turbine technologies. For aviation, I think it does require a lot more work because of the issues with regards to storage and other things. But I think the midterm pathway for hydrogen economy here, it's been looked upon, is about $3 to $4 per kg, which would afford land-based gas turbines as one of the option. And you could already see that happening because there are quite a few what you call as big petrochemical owning companies trying to set up large, huge megawatt scale electrolyzers. An electrolyzer is already being looked upon as one of those technologies for a gigafactory, which is going to be set up probably in the large numbers in the coming years.
Oh, that was great. Thank you. So let's talk a little bit about the heat exchanger, the supercritical CO2 heat exchanger. There's a question here around, there's been some discussion around the Alum Cycle, which uses oxy-fuel combustion and, for ground power applications. In fact, there's, I think, a few demonstrators that are being built globally. So have you thought about kind of those types of concepts and where and how those might integrate with the gas turbine?
Yeah, I mean, we have not really investigated much into it. We have heard about and looked into the Alum Cycle, although rather cursorily. There are quite a few oxy-fuel based systems that's being looked upon. So at this point in time, we have not really looked upon it in depth to comment on the viability or non-viability of such cycles, but would definitely be of interest as we move forward in the next phase of the project. In the first phase, we are primarily looking at the early stages of SCO2 integration. One of the key technology piece that we are trying to validate is utilization of additive manufacturing as a method for handling SCO2, because additive manufacturing has so far been mostly deployed in low pressure applications, whereas with SCO2, you do end up with fairly high pressure. So that's one of the key elements that we are looking to validate. But I think in the next phases of the project, this certainly would be of interest for our grouping here.
Satya, we have experience with high pressure, additively manufactured, high temperature.
Okay.
We've been doing that in Agnicol and stuff.
Okay.
Yeah, I think moderate pressures with the GE project that we do, like about 3-4 bar, but plan to do up to about 70 bar combustion with Inconel 3D.
Inconel based materials. Okay.
Sounds good. Actually, another question popped up. You talked about sort of the engagement of this program with industry, but there's also sort of the regulatory side of and getting regulatory approval from the organization. So, have you talked about or thought about or had conversations with Indian regulatory agencies that would actually have to approve these concepts for flight?
Maybe I have not done it, Satya.
Yeah. Right. So no, I think our regulatory agencies actually follow what either FAA or EASA do. They don't really necessarily do something that's other than what FAA or EASA do. If they have to do this, they will probably have to do separate tests. And I think in our country we have better line of sight to getting it certified by the military certification agency, CEMILAC, more than the civil certification agency. So I think the first point of call would be with the FAA.
Got it.
So Tim, maybe you can help us with that.
Thank you. You bet. No, it's an interesting problem. There's a question here. I'm just going to read it out loud. It says, do we generally do water flow tests on supersonic gas turbine rotors? If done, is there any history available on breakage of blades due to cavitation?
I'm not take up to answer this question. Maybe Nagbhushan?
Probably not. I don't think we'll do that.
I don't know who will be able to answer that. I'm not sure of that water flow test on supersonic gas turbine rotors.
I'm not aware of any such tests. Only for the aircraft. I'm aware of any of these kind of tests, but not of. I'm not aware of any tests being done, saying most of this Indian manufacturing companies for this, water intake tests, and any issues of cavitation in that context. Yeah. Maybe like GE has more, they do all the tests, right? We use the designs or something, but yeah, they do the tests. If they have anything to comment on, like they can add. but as far as I'm aware, like I'm not aware of it.
Okay. Let's go back to this discussion of partners and collaboration. We talked about industry. We just talked about regulatory. What about sort of international collaboration? Obviously, there's a lot going on in Japan, in Europe, the United States,
even in the US.
What's kind of that strategy or plan for collaborations, and are there exchanges planned and things like that?
There is plan for exchange programs. We will just come back to Tim and also go to Jackie O'Connor and maybe go to Japan guys as well. So
well, Santosh Shanbog is on the call, so you want to probably include him.
Santosh Shanbog is on the call. Okay.
Yeah. He's been asking questions.
Oh, he's the one who asked that alum cycle question.
Right.
Yeah, I'll include Santosh.
Tim, the quick answer is we will just tap the Georgia Tech mafia. I'm just kidding.
Okay, here's another question. I guess I think the test article you're developing is 12 bar, if I remember that correctly. And modern flight engines are, civil at least, are running at 50 plus atmospheres. Can you just talk a little bit about how you are thinking about kind of scaling the physics and what that looks like for the obviously 12 bar is a pretty impressive facility, but moving from there to the even more extreme conditions of modern civilian flight engines?
Yeah, basically we agree that the actual conditions are much higher pressures. There are two constraints. One is we can do only this much in first phase. When we go to the second phase, maybe we'll aspire to go to higher pressures. Second thing is diagnostics. We can be very confident only up to maximum 10 bar, and beyond that, PLIF-based data reduction is going to be fishy in some sense. Like all the lines are going to be broader, and that's going to become more difficult to pinpoint specific details inside that diagnostics. So these are constraints right now, but there are people who have done work all the way up to 20 bar and reported that yes, we have measured concentration at that condition, etc. So we will push up to 20 bar eventually when we go to the second phase. But beyond that, if we want to push it to 50 bar, 60 bar, that's going to be only through modeling, I think. That's going to become much more industry-oriented testing, I believe.
What about, okay, so that's the combustor. What about the heat exchangers, the seals? Maybe talk a little about what conditions are we running at relative to where you think they'll be and how you'll scale from lab to the engine.
So the seals can operate as of now up to 600 Kelvin and 10 bar as per the current capacity of NCCRD air supply. When we go to the outside campus, we can push it to higher temperatures easily. Higher pressures also will be done, a little bit up to 20 bar, etc. That I think is reasonable for the seals area. We will be in the ballpark in that condition. What is the second thing you said? The heat exchanger. There is already higher pressure inside. If we go to higher pressures outside, currently I think we can push it only up to 10 bar in our capacity, but we can go all the way up to 35 bar in NCCRD if we push it a little bit more. Satya Seshadri, you have plans for the external pressure being higher. The CO2 is going to be up to 150 bar, but the external pressure.
Oh, I think as of now, we are only looking at the high pressure CO2 heat exchangers. But other than that, no additional plans as of now.
So as of now, it will only be up to 10 bar air and not going to be much higher conditions.
But Murgi, I mean, we
can push it to 35 bar.
We can, strictly speaking, go up to about 35, 40 bar, but for shorter duration, right?
35 bars is possible for short duration. We can do it. 40 bar.
10 bar is actually continuously possible with the new compressors that are coming up to even 2.5 kg per second, right? Whereas with 40 bar, 35, 20 bar, we can actually go up to about 8 kgs per second for about 1 minute or something.
1 minute, yes.
Yeah, but we don't need to probably go up to 8 kgs per second. If it's much lower, we can go for longer duration, but it will not be it won't be like forever. That's the thing. So we do have that capability.
So the heat exchanger part, yes, we can push it to higher pressures. We can go all the way up to probably 35 bar, which is going to put you in the ballpark anyway.
I think a more general answer to these questions would be, Tim, we will actually do the diagnostics and the experimental capability based on what we have at the facilities that we have at NCCRD. But essentially, this is going to be a collaborative work with, let's say, GE, which means that we do a lot of simulation work and so on that can be validated against the facility capabilities that we have, and then it can be applied to conditions that are more realistic, a little bit more than what we have. So effectively, we are looking at closer to realistic conditions. That's a point.
Okay, great.
I want to just dial back to that previous question where we kind of left it about the international collaboration. I think Murgi was beginning to say that we have programs for exchange students and exchange faculty, but I think it's also dovetailed along with this what we call as WIFEs, which is YIFs, young international faculty, right? And so we are actually looking at attracting people who are even a postdoc plus, so that they will become like international faculty, on our campus, right? So that's a very, very active program that's as part of these centers, the Institution of Eminence, Center of Excellence programs. So we have these two possibilities. One is an exchange visits at the level of students and faculty. The other one is the young international faculty in residence that we can actually support over here. That said, I think the international spread that we can actually achieve, or not only in the US, which we were joking about, but we would be very serious about really reaching out to as many people as possible. And plus, we have like lots of European contacts in gas turbines, as you know, as well. And then we can actually go to people like JAXA in Japan and a few other Japanese universities. In addition, I think in this particular COE, because of GE's involvement, and GE is actually an international multinational company, which means that they have not only offices in the US, but also in Germany and other places, including India. So we will also be looking at who they are really interested in bringing in, so that the cooperation will actually be a lot tighter with the industry, right? So that's a kind of flavor that we think we will be following as far as the international cooperation is concerned.
Great. Let's talk a little bit more about hiring. There's a question here on when are you planning on hiring professionals and young faculty, and what's that timeline?
Okay, we are already hiring people who are going to work in the project. For young international faculty, there is a particular procedure that we have to follow. If there is somebody interested, they can contact us and we'll start the process along with you, and then we'll go through the procedure as prescribed by the institute. Since it is going to be like equivalent to a faculty in the department, so just to go through the regular procedure as given by the institute that we will have to follow. It can be done even now.
Great. There's a question here about 3D printing as well, and particularly on the seal side. You talked a little bit about additive. There's a lot of really exciting things around additive associated with heat exchangers and with combustion and fuel injectors. What about on the seal side? Is there sort of an additive plan for leveraging additive for better sealing strategies?
Professor Shekhar. Yeah. Professor Shekhar?
Yes, I'm here. Yeah.
Yeah, so the question had to do with, is there a plan to explore the use of additive manufacturing around seals and seal technology?
I don't think so. GE can answer to that. GE? We don't have any idea of that additive manufacturing there.
I'm hearing seals being printed on shaft only now. I'm not sure of that. But
no, I don't think
GE guys, do you guys have any?
No, as far as my knowledge goes, yeah, it won't be additive manufacturing.
In fact, the company specifically says that they are doing this in space vehicles.
in space vehicles. Okay.
Yeah.
So
anyway, I guess just
the
probably the takeaway is to encourage the center and the center directors to explore the potential of additive across all the verticals.
All the verticals.
I think is the takeaway, Professor Murgy.
There is going to be electrical version also. There is going to be additive manufacturing in there. That much.
Absolutely, absolutely. Well, I think I'm just looking at the time here, and I guess it's about 10:50. Well, it's about 55. Well, okay, in Atlanta, it's 10:55, and so I think I'll turn it back over to Professor Morgan Andom to close us out.
Thank you, Tim. If you have to leave, you said you have some other meetings just after this. So if you have to leave, maybe you can leave, and I'll still continue answering questions in here. Is that what you want to do?
Oh, I'm sorry. I thought this session was over now.
It's supposed to be over now. If there are some questions, we'll just still keep answering. It's fine. But
yeah, we don't have a hard stop.
Don't have much questions here.
Respect your commitments. If you would like to leave,
I think Tim has pretty much posed all the questions.
Yes, pretty much all the questions are answered. So we'll just say, is there any other comments that's left? There is. That is all, I think. I guess. So thank you, Tim, for moderating this session. Thank you all for coming for this particular event and making this a success. There were a lot of participants, and still there are around 100 participants out there. That's pretty good turnaround. So thank you all for coming. Over to you, Richu.
Thank you, Professor Muruganandam. Thanks a lot, Professor Tim, for being with us today. It was our pleasure to host you and to have you here answering all of the questions and being with us today. Thanks to all of the faculty from IIT Madras who is with us. We have a big panel here with us today. Also, thank you to the GE team who is here. It's our honor to collaborate with you and to take this initiative forward. Thanks a lot again, Professor Muruganandam. I'm sure the participants really enjoyed the webinar. It was, you've answered so many questions and gotten really in detail into it. So thanks a lot. Thank you to everybody. Thank you to the participants. Have a good night. Thanks. Thank you.
Thank you.
Good night.
Thank you all.
Thank you. Thank you.
Thank you. Bye.
Thank you.
See you, Murgy.
Bye, Tim.
Satya, good to see you.
Bye. Yeah, good to see you.
Congratulations on the nice center. And next time I see you, I hope I'll be in Chennai. I would love to come visit you guys again.
You better come here as soon as possible. You'll see a lot of exciting things happening.
There is a lot more change after you came last time.
And bring your family here.
Yes,
we'll be very glad
absolutely.
to see them.
Yep, definitely. Okay, take care.
All your daughters.
Absolutely. All right, bye-bye.
Bye-bye.
Thanks, everyone. Bye.
Thank you. Bye. So Richu, you will stop the recording and all, right?
Yeah, Naresh will end the webinar.
Yeah. Okay.
Thank you.